So let's start with our new subject, that is about the number theory. So here I am going to discuss today is about the congruence. So what is congruence? The basic concept is basically Gauss introduced the concept of the congruence. So the basic definition of the congruence is if m is greater than 0 and a, b and m belong to some integers, we say that a is congruent to b modulo m. If m divides a minus b, then we can write it a is congruent to b mod m. So this is the basic definition of the congruence. That means if we have two integers a and b and m is some other integer, then m divides if a minus b, then I can say that a is congruent to b in modulo m. So also we say that a is the residue of the b and b is the residue of a. And if m doesn't divides a minus b, then we can say that a is incongruent to b modulo m. That means a is incongruent to b modulo m. Here is the example of the congruency. Here I take the example that 4 in modulo 3. So that means 4 is congruent to 1 in modulo 3. So by applying this definition, that means 3 divides 4 minus 1, like this. So that means 3 divides 3. So this condition holds by the definition of the divisibility. This is a true statement that 3 always divides 3. Or I can say that if I I can say by simple division, I can say if 3 into 3 ones are 3, so that means the remainder is 1. So I can write as 3 divides 4 minus 1. So that is basically you can say 4 is congruent to 1 in modulo 3. So here is the other example that 11 is congruent to 2 in modulo 3. So if by using this term, I can say by division method, I can say that 3 divides 11 minus 2. So 11 minus 2, that is basically 9. So that means 3 divides 9. So this is a true statement. So this is, I can say that 11 is congruent to 2 and 4 is congruent to 1. So there are many examples of congruencies you find here. So the next is I can say that a minus b, that is equals to km. K is some, you can say some integers that multiplied with the m, and this result divides a minus b. Here is the theorem about the congruency, that is the congruence relation in integers is an equivalence relation. That means the congruence relation is basically is just like an equivalence relation. So proof, I'm going to prove it here. First one is the reflexive property, that is with itself. So since for all a belongs to z, I can say that m divides a minus a. So that means a is congruent to a in modulo m. So this condition satisfied here in the congruence relation. Next is the symmetric property. That means if a is congruent to b in modulo m, then b is congruent to a. So we have to prove this condition, that if for a b belongs to z and m greater than 0, a congruent to b modulo m, then b congruent to a modulo b congruent to a modulo m. This is the condition, we are going to prove it here. So since as we know that a is congruent to b in modulo m, then I can say that m divides a minus b, that means m divides minus b minus a. So we previously discussed this result in the properties of the divisibility, that if m divides a, then m divides minus a. So that means m divides minus ba, so I can write it as m divides b minus a. Like this, by using this property, I can say that m divides b minus a. So this implies b is congruent to a modulo m. So this is the condition, we are going to prove it here, that if a is congruent to b, then b is congruent to a in modulo m. So this property also satisfied. Now the third property is transitive property. For a, b, c belongs to integers and m greater than 0. So first condition is if a is congruent to b in modulo m and b is congruent to c modulo m, then I can say that a is congruent to c modulo m. So this is the condition here. So from, I can say from 1 and 2, from this equation I can say that m divides a minus b, and from second equation I can say that m divides b minus c, like this. Now I can say that m divides a minus b plus b minus c. I can write it as like this by using the property of the divisibility, that if m divides a minus b and m divides b minus c, then m divides addition of these two values. So m divides a minus b plus b minus c, b cancel out, so I have only that result that m divides a minus c. So that means by applying the definition of the congruence, I can write it as a is congruent to c in modulo m. So here this is the third property, transitive property. So this property also prove, hence the congruence relation in Z is an equivalence relation. So this is the first theorem. Here we prove some, you can say, congruence relation in integers is basically an equivalence relation. Next theorem is a is congruent to b modulo m if a and b have same remainder after division by m. That means both have the same remainder if we divide it by m. So here I am going to use that division algorithm or the Euclid, I can say Euclid lemma. So here first of all I am going to use this condition, that suppose that a is congruent to b modulo m, then by the definition of the congruence I can say that m divides a minus b, then there exists an integer q belongs to z. Here is, now I am applying here the definition of the divisibility, that if m divides a minus b, then I can write it as a minus b, that is equals to mq. Now further q is basically some integer. This is the equation 1, and let I'm going to say that a, that is equals to mq1 plus r1, r is some remainder that is less than m, and b, that is equals to mq2 plus r2, where r2 is some remainder that is less than m, and here q1, q2, r1, r2 belongs to integer. Now further is I am going to do is subtracting these two equations, that a minus b, that is equals to mq1 plus r1 minus mq2 minus r2, like this. Now further taking m common from this term and this term, m into q1 minus q2 plus r1 minus r2. Now further is taking this equation of the this expression of the m on the other side of the I can say equal, so mq minus mq1 minus q2, that is equals to r1 minus r2. So I can say that I can write this equation like m divides r1 minus r2. This is also the, you can say, the theorem about the divisibility. We discussed this result earlier. So by this result I can write this equation like m divides r1 minus r2. So here is some note, that if m divides r and r is less than m, then r must be equals to 0. Now further is condition given here, that here r1 minus r2 is less than 1. That means r1 minus r2 is equals to 0. That means r1 is equals to r2. So this is the condition here, that the remainder is equal. So that means the remainder of a and b is same. Now conversely, what we have to do is suppose that a and b have same remainder. Here I take this result and prove that this a and b have the same remainder, like I prove it here, that r1 equals to r2. That means a and b have same remainders. Now in the next step, in the conversely, I can say that I suppose that a and b have same remainders, and I prove that result a is congruent to b. So if a and b have same remainders, I can write it like by using the Euclid theorem, that a, that is equals to mq1 plus r, and b, that is equals to mq2 plus r. Now subtracting these two equations, I can write it as a minus b, that is equals to mq1 minus q2 plus r minus r. Cancelling this r, so I have only that result a minus b, that is equals to mq3. Now by the definition of the divisibility, I can write that m divides a minus b. That means by, and now further applying the definition of the congruence here, so that means a is congruent to b modulo m. So this is the condition here. I take this thing that A is congruent to B and prove that A and B have the same remainder. And in the converse, I take that A and B have same remainder. Then I prove this that A is congruent to B. So this is the proof of this theorem. Now further is the third theorem, that if A is congruent to B modulo M and C is congruent to D modulo M, then we have to prove this condition that A plus C is congruent to B plus D modulo M, A minus C is congruent to B minus D modulo M, and AC is congruent to BD modulo M. So for the first step, when A plus C is congruent to B plus D modulo M, I am going to solve this first step. So for this, I take this two condition that A is congruent to B and C is congruent to D. So if A is congruent to B modulo M, by the definition of the congruency, I can write it as M divides A minus B. This is the equation 1. And also if C is congruent to D modulo M, then I can write it as M divides C minus D. This is the equation 2. Now from 1 and 2, I can write it as M divides A minus B plus C minus D. So M divides A plus C minus B plus D, arranging this. So that means A plus C is congruent to B plus D modulo M. Simply I can write it as. Now further property is, what we have to do is A minus C, that is congruent to B minus D modulo M. Like this. If A is congruent to B, I can write it by the definition of the congruency that M divides A minus B. This is the equation 1. And the second condition is if C is congruent to D modulo M, then M divides C minus D. This is the equation 2. Now from 1 and 2, I am going to subtract these. So M divides A minus B minus C minus D. So multiplying this minus sign with C and D, I got this result that M divides A minus C minus B plus D. Now arranging this, I got M divides A minus C minus B minus D. So that means I can write it by the definition of the congruence that A minus C is congruent to B minus D modulo M. So this result also satisfied. Now the last result is AC is congruent to BD modulo M. So again, I'm going to follow those steps. So if A is congruent to B modulo M, then I can write M divides A minus B. This is the equation 1. And by the definition of the divisibility here, I can write A minus B, that is equals to MQ1. And further, by the Euclid lemma, I can say that A, that is equals to MQ1 plus B. This is the equation 2, or I can arrange this equation. Okay. And the further is, if C is congruent to D modulo M, then I can write it as M divides C minus D. Now further, by the definition of the divisibility, I can write it as C minus D, that is equals to MQ2. Now from 2 and 4, I can say that multiplying these two equations, A and you can say C, so that is MQ1 plus B into MQ2 plus D, like this. Multiplying this, so MQ1 into MQ2, so that is M square Q1 Q2, and MQ1D further is MBQ2 and BD. This result, sorry, here is Q2 not Q1, this is my mistake. Now further is arranging this, I got that result. This BD is I'm taking it from the other side of the equation, so AC minus BD, that is equals to M square Q1 Q2 plus MD Q1 plus MB. Here is Q2 basically. So the further thing is, if this is the result, so that means I can write it as the product of M and Q. So A, that means M divides, I can say AC minus BD by the definition of the divisibility. So M divides AC minus BD, that means by the definition of the congruence, I can say that AC is congruent to BD modulo M. So this is the basic journal theorems about the congruence. So we discuss here what is the definition of the congruence, and some example of the congruence, and also some you can say some results we prove here and some theorem we prove here about the congruence.